For an exceptionally prolonged period, individuals have speculated about what existence might be like on other worlds. Thanks to the James Webb Space Telescope, the most advanced telescope available, this query can finally be addressed. While scrutinizing the nearest stellar system to us, Proxima Centauri, which is merely 4 light-years away, scientists have detected several unusual anomalies from one of the planets in the system, Proxima B. These anomalies, referred to as artificial illumination, have puzzled the most brilliant minds in conventional science. But what are they? Do these lights indicate the presence of intelligent beings on the planet? Join us as we explore the James Webb's astonishing discovery of city lights that could change everything. The only life we currently recognize is on Earth. Since the dawn of civilization, humans have wondered if there is life elsewhere in the cosmos. To pursue such an interstellar quest, American astronomers Jill Tarter and Thomas Pearson initiated the search for extraterrestrial intelligence, SETI, project in 1984. The organization's goal is to capture radio signals from space. Radio waves can travel longer distances and are therefore more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Sierra Nevada mountains of California, as they are less scattered or absorbed than other types of radiation. However, in the past 3 decades, no clear extraterrestrial signals have been discovered. Consequently, the successful launch of the James Webb Space Telescope has advanced the search to explore a variety of distances and unseen planets orbiting distant stars. The largest telescope on Earth, currently drifting approximately 1 million miles from our planet and equipped with extremely sensitive detectors, will be utilized. Previously, no known planets existed beyond those in our solar system. However, since then, over 4,000 exoplanets have been discovered orbiting other stars. According to NASA, the universe may contain trillions of exoplanets. The first indications of life beyond our solar system may be found in alien vegetation. The Galileo spacecraft redirected its instruments toward Earth while traveling to Jupiter and detected a clear sign of plant life. The instrument observed the vegetation red edge, a mix of red and infrared light reflected by plants. For instance, a planet like Earth, covered in lush vegetation, should exhibit a strong and easily detectable red edge. The JWST will measure the red edge of distant Earth-like planets situated in the habitable zone around stars. These could be significant indicators of life in the exoplanet's atmosphere. When sunlight passes through a planet's atmosphere, the JWST might detect it as it enters the atmosphere. The light's missing frequencies would then be identified through spectroscopy. Ions and atoms in the atmosphere absorb specific frequencies, creating a unique fingerprint that the JWST can detect. This process could be used to learn about the atmosphere's composition and the potential for life. Most likely, life could exist on Earth-sized planets with atmospheres similar to ours, featuring oxygen, nitrogen, and carbon dioxide. By searching for substances that are not normally present, one might identify technological life. Chlorofluorocarbons, CFCs, created for refrigeration and cleaning, could be detectable to extraterrestrials observing Earth's atmosphere from afar. If the JWST identified CFCs in planetary atmospheres, that would be a clear sign of civilization. In fact, life on exoplanets might not resemble life on Earth. Sometimes even natural life, like extremophiles, can appear alien. This group of organisms, mostly microbes, can survive in conditions where other life forms would perish. Some can endure temperatures up to 250 degrees Fahrenheit, some can withstand cold as low as -4 degrees Fahrenheit, and others can survive in highly acidic environments with pH levels below 3. Others can be found on Earth where we wouldn't expect life at all. However, since planets like Earth are more likely to support life than planets with extreme temperatures or acidic conditions, it may be prudent to start with those first. Prime candidates might have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are rarer and generally have shorter lifespans in the universe. The probability of studying planets orbiting red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. There is more potential for the development of life and evolution to create complex organisms because these stars have longer lifespans. Located about 40 light-years from Earth, the TRAPPIST-1 planetary system will be the focus of JWST's initial mission. It orbits a cool red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets in the so-called habitable zone might have liquid water on their surfaces. Despite having a much smaller and cooler mass than our Sun, the TRAPPIST-1 star emits light similar to that of Earth due to the close proximity of its planets. The most plausible opportunity to observe city lights outside the solar system is Proxima Centauri, a red dwarf star situated 4.25 light-years from the Sun, our nearest star. Proxima is several times dimmer than the Sun, so a planet would need to be much closer to it than Earth is to the Sun for it to support life with liquid water. In August 2016, astronomers discovered a planet with 1.3 times the mass in the habitable zone, or Goldilocks zone, where the light intensity is just right to permit water to remain liquid. Proxima B orbits Proxima Centauri. If feasible, Proxima B might be an airless, lifeless planet, considering that it orbits its red dwarf star, Proxima Centauri, at a distance of only 4.6 million miles. Proxima B is in a close orbit that exposes it to intense solar winds that could strip away its atmosphere. It also receives enough sunlight for temperatures and liquid water that are nearly identical to those on Earth. Due to its proximity to the star, Proxima B is believed to be tidally locked, always showing the same side to the star. Like Earth, Proxima Centauri has about 18% the mass of the Sun and shines much less brightly than one might expect for a planet so close to its star, only 5% of the Sun's brightness. This might be expected to be a superhot cinder, though liquid water could exist on Proxima B as long as the planet has an atmosphere to retain heat, since the total energy reaching it from the star is only 65% of what Earth receives. Currently, the planet is not particularly inviting to life. It is probably tidally locked, meaning it always faces the same direction towards the star, causing significant temperature variations. The planet also receives 100 times more high-energy radiation than Earth does due to its proximity to Proxima Centauri, including X-rays and ultraviolet light. Proxima B is also bombarded with high-energy particles during star flare-ups. Unless it has a protective magnetic field like Earth, however, there are some plausible conditions that could make it a habitable world. Models suggest that the atmosphere of tidally locked planets might be prone to rapid breakdown due to the freezing out of volatile gases on the night side. A planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Since we know nothing about Proxima B's volcanic activity or magnetic field strength, we can't even estimate whether the planet has an atmosphere. However, since an atmosphere implies the presence of CFCs and the two combined suggest the presence of life, we are eager to find out if Proxima B has an advanced civilization. It could have solar panels covering the day side to generate power to illuminate and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has ignited a race to determine whether it transits its star as seen from Earth. These transits would enable scientists to determine the planet's size and mass, which would then allow them to learn its density. Knowing this would confirm the planet's rocky composition and provide information on the materials used to form those rocks. During a transit, starlight could reveal the nature of the planet by passing through its atmosphere. However, the probability that the orbit will be aligned for researchers to observe a transit is only 1.5%. The star's tendency to flare also complicates matters. Astronomer David Kipping of Columbia University says the star is unstable. As a star's heat makes a rocky planet absorb sunlight and re-emit it as infrared light, rocky planets produce a unique type of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope was specifically designed to study infrared light. Proxima B's infrared heat signature is crucial for identifying the planet's atmosphere. Furthermore, the infrared part of the spectrum has strong signals for water. The JWST will be able to detect artificial illumination on Proxima B's night side, even if it were as faint as what our civilization currently uses on the night side of Earth. The JWST could detect artificial lighting as long as it was confined to a frequency band that is multiple times narrower than starlight. Proxima B's day side is heavily covered with solar panels. Due to its unique spectral edge capacity to reflect starlight as Proxima B orbits its star day in and day out, Its day and night temperatures would be crucial for determining how much heat is still retained. JWST will monitor Proxima B's night side. Despite the planet being extremely cold, JWST's infrared vision will help find artificial light. When light from the night side passes through the atmosphere, researchers will use JWST to analyze it. Investigating the possibility of alien life has intrigued researchers and enthusiasts alike for many years. The development of space observatories, such as the James Webb Space Telescope, JWST, has equipped scientists with unparalleled instruments for exploring distant worlds and their potential to sustain life. Beyond Proxima B, there are several other fascinating targets in the quest for evidence of life. A notable example is the TRAPPIST-1 system, which features multiple exoplanets within its habitable zone, making it a prime candidate for further investigation. The TRAPPIST-1 system is particularly captivating due to its arrangement of 7 Earth-sized planets orbiting a red dwarf star. These planets are of considerable interest because their closeness to their host star places them in the habitable zone, where conditions might support the existence of liquid water. Given that liquid water is a crucial prerequisite for life as we understand it, examining these planets could yield insights into the potential for alien life. The JWST, with its sophisticated infrared capabilities, is ideally suited for studying the atmospheres of these exoplanets. By analyzing the infrared spectrum of light that passes through a planet's atmosphere, researchers can identify key molecules such as water vapor, methane, and carbon dioxide. These molecules are often linked to biological processes, and their detection could signal the presence of life. Additionally, the JWST's capability to capture detailed images and spectra enables the examination of atmospheric composition and weather patterns, which can provide clues about the planet's climate and its potential to support life. Another intriguing target is the exoplanet Kepler 452b, often dubbed Earth's cousin. This exoplanet orbits within the habitable zone of a star similar to our Sun, with dimensions and an orbit comparable to Earth's. Kepler 452b offers an exciting opportunity for researchers to investigate a planet that might have conditions similar to those on Earth. The JWST's observations of this planet could offer valuable data on its atmosphere and surface conditions, enhancing our understanding of how common Earth-like planets might be in the galaxy. In addition to studying individual exoplanets, the JWST will also advance our knowledge of planetary systems as a whole. By examining the frequency and distribution of exoplanets in various types of star systems, researchers can gain insights into the formation and evolution of planetary systems. This information is vital for determining the likelihood of finding habitable planets and understanding the broader context of our place in the cosmos. The search for alien life also extends to the investigation of moons within our own solar system. For instance, Europa, one of Jupiter's moons, is thought to have a subsurface ocean beneath its icy surface. The possibility of life in such an ocean is a topic of intense scientific interest. Missions like the Europa Clipper, scheduled to launch in the near future, aim to explore this moon in detail. The JWST could play a supplementary role by studying the outer regions of our solar system and detecting any potential signs of activity or atmospheric interactions. Furthermore, examining comets and asteroids offers additional opportunities to understand the fundamental building blocks of life. These objects are regarded as remnants from the early solar system and may contain organic molecules or other compounds that could illuminate the origins of life. Observations of comets and asteroids using the JWST could reveal the presence of complex organic compounds and provide insights into the conditions that might have led to the emergence of life. The pursuit of understanding life beyond Earth also involves exploring the potential for life in extreme environments, both on other planets and within our own solar system. For example, the study of extremophiles, organisms that thrive in harsh conditions on Earth, offers clues about the types of environments where life might exist elsewhere. By understanding how these organisms survive in extreme conditions, researchers can develop models for what kinds of environments might support life on other planets. Additionally, advancements in artificial intelligence and machine learning are increasingly being used to analyze astronomical data. These technologies can process vast amounts of information rapidly and identify patterns that might suggest extraterrestrial signals or other phenomena. The integration of AI with the data gathered by the JWST and other observatories could enhance our ability to detect and interpret potential signs of life. In summary, the exploration of exoplanets and the search for alien life is a multifaceted endeavor that involves studying a broad range of celestial objects and environments. The James Webb Space Telescope, with its advanced capabilities, is positioned to make significant contributions to this field. By examining exoplanets within habitable zones, studying planetary systems, exploring moons within our solar system, and analyzing comets and asteroids, researchers aim to broaden our understanding of the potential for life beyond Earth. As technology continues to advance and new missions are launched, our knowledge of the universe and our place within it will undoubtedly deepen, bringing us closer to answering one of humanity's most profound questions. Are we alone in the universe?